So, yes, can you understand this thing, what we are doing? Because if you have missed the previous lectures, definitely you cannot understand anything in this. If you attended all the previous lectures, you can easily understand this flow, that how we are doing this tracing. Because in your exam, you have to attempt with similar kind of examples, and the weightage will be 12 marks. One example, the weightage will be 12 marks. Write down the rules of PDA and you have to trace for the given string. Okay, so if there is no query, we can proceed further. So now, can anyone explain what we are doing here? It is a general palindrome. Now it is a general palindrome. Right? X is a palindrome. So we are talking about odd length palindrome, even length palindrome, both. So can anyone tell what we are doing in rule 1? Can anyone write in the chat window? Rule 1. What we are doing in rule 1? We have two different moves in rule 1. Can anyone explain in the chat window what is rule 1? It is a general palindrome. That means it can be odd length, it can be even length. Right, we are pushing A on the stack and we are ignoring the first A. So this rule is useful for odd length palindrome or even length palindrome. Ignore A. Ignore A rule will be for odd length palindrome, it will be for the even length palindrome. Yes, ignore A rule. I am talking about ignore A. It is for odd length or even length? It is for odd length, because when it is odd length, we are assuming that A can be a middle symbol or B can be a middle symbol. Similarly, rule number 2, 3, 4, 5, 6, up to 6 rules, they are push and ignore rules, as you can see, from 1 to 6, right? All the rules 1 to 6, they are push and ignore rules, and they are used in odd length palindrome. Now rule number 7, 8, 9. Can you see rule number 7, 8, 9? So what is the significance of that rule number 7, 8, 9? Yes, can anyone tell what is the significance of rule 7, 8, 9? Right, when it is a even length palindrome, we have to assume null as a middle symbol. We have to assume null as a middle symbol. So we require ignore rules for the null. Right, we require ignore rules for the even length palindrome also. So this 7, 8, 9 are also, right, rules 7 to 9 are also ignore rules for the odd or even length palindrome. Right? So basically rules 7 to 9, 7, 8, 9. Q0 null, Z0. We are ignoring the null. Q0 is converted to Q1. So rules 7 to 9 are also ignore rules for the even length palindrome. Q0 null, Z0. It is Q1, Z0. It is a even length palindrome. Rule 10 and 11. They are pop rules. The rule number 10 and 11 are the pop rules. And last rule number 12, it is for acceptance. It is for acceptance. So we can see that there are total 12 rules. Okay, so now, yes, can anyone explain this first part? So now I want to recognize this BAAB. I want to recognize BAAB. I don't know whether it is a odd length palindrome or it is a even length palindrome. So can anyone tell what we'll do first? BAAB. We don't know whether it is a odd length palindrome or it is a even length palindrome. We don't have any idea. So what we have to do? The first thing is we'll push B, first option. Second, it can be odd, it can be ignore B if it is odd length. And third option, we have to ignore null. We have to put null as the first position because if it is a even length palindrome, then we have to check null at every position. We have to check null at every position. Right? So we have three things. Push B. So as you can see here, that leftmost branch, we are pushing B on the stack. We are pushing B on the stack. Q0, then AB and BZ0. Leftmost branch, Q0, AAB and BZ0. We are pushing B on the stack. So now the middle branch. Okay, so what middle branch does? Can anyone tell? Middle branch. It is assuming that it is an odd length palindrome and it is ignoring B. It is ignoring the B with the assumption that it can be an odd length palindrome. And it can be only B. It can be only B. Now the third branch. What third branch does? It will assume that it is a even length palindrome. It is an even length palindrome. Right? So it is considering null at the beginning. So it is ignoring the null. So basically, it is treating that it is the end of the push operation. It is putting null at the beginning. And it will convert the push operation to pop operation. That is what we are doing in the first step. Now let us go to the next level. So as you can see that second and third branch, right? Second and third branch will crash because second branch you can see a Q1 AAB Z0. So we can only apply one rule from the Q1 state, Q1 null Z0. It is Q1 null Z0. So that Q1 null Z0 will give us Q2 AAB Z0. That gives us Q2 AAB Z0. So it will crash. Similarly, the third branch, the rightmost branch, Q1 null Z0. That will give us Q2 AAB Z0. So it will also crash because we have not consumed the input. So only the leftmost branch will survive. Is it clear? Only the leftmost branch will survive here. And we have to explore that branch. So now can anyone tell what we are doing in level 2 in the leftmost branch? The leftmost branch, level 2. We'll push the second A on the stack. Okay. Then we are ignoring that A as a middle symbol. And then third one, we are considering null. We are considering null and we are changing to state Q1. So again, you can see at this level, the middle branch will crash because Q1 null BZ0. So Q1 null BZ0, right? We are assuming null there, or Q1 AB. So there is no such rule. Q1 AB is not there. Q1 null BZ0 is also not there. So that branch will crash. The second level, middle branch. Similarly, the second level, third branch. The second level, third branch. It is Q1 AAB and BZ0. So that will also crash because Q1 AB, there is no such rule. Similarly, Q1 null B, there is no such rule. So only the leftmost branch will survive. Only the leftmost branch will survive here. So let us further extend it. So again, we have three possibilities: the leftmost branch, middle branch, and the rightmost one. So in the leftmost one, we are pushing a third symbol on the stack. In the middle one, we are ignoring the A. So it is Q1, B, AB, Z0, and it will crash there. And the third branch, which is our actual branch, because it is a even length palindrome. Because it is a even length palindrome. So it is Q1, then AB, AB, Z0. So we are assuming null after two symbols. We are assuming null after two symbols. So state will change from Q0 to Q1. Q1, AB, AB, Z0. This Q1, AB, AB, Z0. I hope you are getting this flow. Yes? I hope you are getting this flow, what we are doing here. Right? So what will happen with the left branch now? Will the left branch will succeed? The leftmost branch will not succeed, right? Then middle branch will not succeed, right? So as you can see here, this is the remaining part, right? The leftmost one will crash. Then you can see only the last branch, the rightmost one, only the rightmost one which will succeed, because we are assuming null after two symbols. So Q1 AA, it is a pub operation. So we'll get Q1 B and B. Again, it is a pub operation. So we'll get Q1 null Z0, the rightmost branch. Q1 null Z0. And it will give us Q2 null Z0, and it will succeed. It will succeed. Remaining all the branches, because still we have to do all other operations like push and ignore. But all these branches will crash. All these other branches will crash. So I hope this example is a very good example, which is covering both odd and even length palindrome. So I hope you are getting this. Any query in this? If you have any query, you can ask. Also, your marks of TAFL are uploaded on the e-governance site. So I think you have got that. Yes, have you got your marks of TAFL? So that is also you can check. Site is working. I think the issue is with the browser. If you try some Microsoft Edge, then it will allow you to see the marks, because that is what I have verified, that in Microsoft Edge we are not facing any issue. We are facing the issue with Google Chrome. You can try out that. Yes, anyone has checked the marks? Okay, so you can try out that Microsoft Edge and it will work properly. Right? Okay, so now let me share another slide. Let us proceed further. So far we have not defined the term, that is, what is a push down automata actually, right? So far we have defined only, we have solved the examples. If you want to define it, what we can say about the push down automata, that is the most important thing. We have defined the finite automata having 5 parameters, a set of states, input symbol, we have a transition function, set of accepting states. That is how we are defining a finite automata. So similar to that, we'll define the push down automata now. So as you can see here, there is a definition of push down automata. It is having a 7 parameters. It is having 7 parameters, a Q, that is a set of states, the sigma, that is the input alphabet. We have another special symbol, which is known as tau. It is a Greek alphabet. Right? The third is a tau. It is not T. You can see it is not T. It is a Greek alphabet tau. Like alpha, beta, gamma, it is tau. So Q, sigma, tau. We have a Q0, a starting state, a Z0, a special symbol on the stack, A, which is a set of accepting state, and delta, which is a transition function. So now you can see the definition of delta, that our transition depends on 3 parameters. Our transition depends on 3 parameters: the current state, input alphabet, union null, because sometimes we are taking null symbol as an input. So, and the third parameter is top of the stack, a tau. Right? So T is indicating a stack, right? So top of the stack alphabet. So based on these 3, we are writing the move, and that move will be what? It is a set of finite subset of Q cross tau star. So basically it is telling that it is Q cross tau star. So in the move operation, we have the state and the stack alphabet. Whatever moves we have written so far, what we have written? The move is having a state and the stack alphabet. We are sometimes writing Q0 AZ0. Sometimes we are writing Q0 AA. Sometimes we are writing Q1 null. So it is a combination of state and the stack alphabet, tau star. So this is what we are defining the push down automata. A set of states, input alphabet, stack alphabet, tau, Q0, a starting state, Z0, special symbol, A, accepting states, and transition function. So it depends on 3 input parameters: state, input, union, null, and the top of the stack, and the output of the transition function. It is not only state, it is not only state, but it is a combination of state with stack alphabet. So combination of state along with stack alphabet. That is how we'll define the push down automata. Okay. So how we'll define the acceptance of the push down automata? So that is the next thing. This is how we'll define the acceptance by push down automata. So we have discussed that also, that when we start the push down automata for any given string x, x is accepted by the machine if we'll start from the configuration, that is Q0 x Z0. We'll start from this configuration Q0 x Z0. Z0 is on the top of the stack, x is your input string which we want to verify, and Q0 is the starting state. And by applying 1 or more steps, right? Or we can say by applying 0 or more steps, because in some case it is already valid, like Q0 null Z0. So Q0 null Z0, right? If Q0 is the accepting state, then it is a valid thing. So by applying 0 or more steps of the machine, we'll reach to a state Q, which is an accepting state. We'll fully consume the input. Input must be fully consumed. And alpha. Alpha means there can be anything on the stack. This alpha belongs to tau star. So even in some examples, if required, we can pop the Z0. Alpha belongs to tau star. So in some examples, we can also pop Z0 from the stack if required. So we can say a string is accepted by the automata if will reach to the accepting state, will consume the full input. And we can say L is equal to Lm. That means the machine should not accept any extra element. The machine should not accept any extra element from the sigma star, and it should not leave any element from the language L. Then L is equal to Lm. Both must have the same set. The set of strings in the language L and the set of strings in the machine M must be equal. None of them can be the superset. All the elements in L must be accepted by M, and no extra element is accepted by the machine. That is how we can say it is acceptance by a PDA, push down automata. Yes, do you have any query? So we have solved 3-4 examples. So I think now you can understand this definition very well. That why it is Q null alpha. We have to reach to the accepting state. We have to consume the full input, and there can be anything on the top of the stack. Right? It is alpha. Alpha can be anything. Okay, so now with this, let us take one more definition. So now we'll differentiate between a deterministic push down automata and non-deterministic push down automata. So if you look at the previous example which we have solved, we can clearly see a non-determinism in the automata, in the general palindrome, because we have 3 different branches. The push the symbol, ignore the symbol, and ignore the null. So definitely it is a non-determinism. It is not a deterministic path. It is not a deterministic path. That we cannot have a unique one path. Right? We are trying all the different paths, similar to non-deterministic finite automata. In non-deterministic finite automata, we have the same thing. We have the same thing. We have different multiple paths. And out of all the paths, only one path will go to acceptance. So similar to that, what we have solved, even length palindrome, right? Or any example in which we have 2 branches or more than 2 branches. When we need a fork system call to check the alternative. So odd length palindrome. Also we have 2 branches, ignore and push. In the even length palindrome, also we have 2 branches, push and ignore null. In general palindrome, we have 3 branches. So all these 3 examples which we have solved are related to non-deterministic push down automata. One most important thing is that the power of deterministic push down automata is less as compared to non-deterministic push down automata. So we can say that NPDA is more powerful than DPDA. NPDA is more powerful than DPDA. That means we can accept more context-free languages. We can accept more context-free languages by NPDA, or we can say NPDA accepts all context-free languages, while DPDA accepts subset of context-free languages. So NPDA accepts all context-free languages, while DPDA accepts subset of CFLs. That is the main difference. So we don't have an algorithm like convert NPDA to DPDA, right? You have done NFA to FA conversion. You have done NFA null to NFA conversion, but it is not possible for push down automata. You cannot have an algorithm which will convert non-deterministic push down automata to deterministic push down automata. So what is the rule? That how we can say it is a deterministic push down automata? We have these 2 conditions. The first one is very straightforward, that for every Q belongs to Q and every sigma belongs to sigma union null, and every x belongs to tau, the set delta q sigma x, small sigma is here, so delta q small sigma x has at most one element. That means there should not be two alternatives. There should not be two alternatives. So as you can see in the previous example, we are writing like this: Q0, A, Z0. Right? We are having two alternatives for that. Q0, A, Z0. And second one is Q1, Z0. So this is not valid in deterministic push down automata. Right? We are writing this Q0, A, Z0. Either you push the A on the stack and stay in the push operation, or second, ignore the A and go to the pop operation. So we should not have two different options. We must have at most one element. So any combination of state, input and top of the stack should not have two alternatives. So when you see two different alternatives, it is not valid. Right? So we should not have two alternatives for any combination of state, input and top of the stack. A second rule is, if there is a null in the input, then the state and the top of the stack should not be used with another alphabet. If you are using null in the input, as you can see in the rule number 2, right? When there is a null in the input, right? If there is a null in the input position, then that state and the top of the stack should not be used with any another state and top of the stack. Right? You have to first focus on the rule in which null is there, and you have to extract the state and the top of the stack. So I cannot use that state and top of the stack with any another input alphabet. Once I am using state and top of the stack both, once I am using a state and the top of the stack with any null, then I cannot use the same state and top of the stack with any another input alphabet. So one example is this: a Q0 null A. It is from the even length palindrome. So once I am using this Q0 null A, which is giving me Q1, I'm ignoring the null. Right? So which is giving me Q0 null A will give me Q1A. So what I have to do, I have to extract null rules, and from that we'll get the state. So here state is Q0 and A is in the input. So I cannot use Q0 and A with any another input alphabet. I cannot use this Q0 and A with any another input alphabet, so that it becomes a deterministic PDA. And deterministic PDA will accept deterministic context-free languages. This deterministic PDA will accept deterministic context-free languages. Now, why this second rule is required? Because null is creating also one branch, or it is creating one more process when we are deriving the, when we are verifying the string. You can see one branch is for the push operation, second branch will be for the ignore the alphabet, and third branch is for the ignoring the null. So null is also creating one branch in the push down automata. Is it clear? So to get a deterministic push down automata, we must have one branch. We should not have a leftmost branch, middle branch, and the rightmost branch. Right? Three branches are not valid in deterministic push down automata. We must have only one unique path. So we have to cut down both the branches. A branch which is ignoring the alphabet, and the branch which is ignoring the null. If we cut down that, yes, here input is null. Right? Here input is null. Right? So when input is null, it is creating also one branch. Input is null means we are assuming null at every position. Input is null means what? It is like a even length palindrome. It is like a even length palindrome. So basically what it tells that once you have input as null, you have to extract state and the top of the stack. You have to find input null from the rule, extract state and top of the stack, same state and top of the stack cannot be used with any other input alphabet to get the determinism. So now using this, let us create some deterministic push down automata. So here you can see the description of that rule, right? These are the rules from the even length palindrome. These are the rules from even length palindrome. So you can see Q0 null Z0, Q0 null Z0. So I can use Q0 and AZ0 if I will use it with some another input alphabet, then it is a non-deterministic PDA. It is a non-deterministic PDA. So Q0 null Z0, it will give me Q1 Z0, ignoring the null. And if I use Q0 AZ0, which will give me push operation, Q0 AZ0. So it will make it a non-deterministic PDA. Similar to that, Q0 null A. Q0 null A, it is a ignore operation, Q1A. It is Q1A. And Q0 AA. So Q0 AA, right? So that is a push operation. So we cannot use that, right? It will make it a non-deterministic push down automata. It will make it non-deterministic push down automata. So you can see Q, small sigma and X. So we are extracting Q and X, and that Q and X cannot be used with any another rule to achieve a deterministic push down automata. Otherwise, it will create a branch. Otherwise, it will create a branch in the PDA and it will make it non-deterministic. So I hope these two rules are telling you that it is a non-deterministic push down automata. I hope now it is clear. This is a representation of rule 2. This is a representation of rule number 2. Is it clear? Okay, so now with this, let us construct a deterministic push down automata. So now here our language is, it is a balanced string of brackets. It is a balanced string of brackets, right? We have valid examples like this. These are the valid examples of balanced string of brackets. We can have nested brackets. We can have a series of balanced brackets. So now, definitely to achieve the goal, what we are doing, that we have to push the opening bracket and it will match with the corresponding closing bracket. We'll push all the opening brackets and we'll match it with the closing brackets. So also null is a valid string Also null is a valid string. So when null is valid, Q0 will be the accepting state in deterministic PDA. In deterministic PDA, when null is a valid string, Q0 will be the accepting state. So from Q0, we'll go to Q1 immediately. From Q0, we'll go to Q1 state immediately and we'll push opening bracket. After that, we have a recursive step. We have a recursive step where Q1 will push any number of opening brackets which we are receiving. It is a recursive step, Q1, opening bracket, and we are pushing opening bracket on the stack. So it is Q1 and double opening bracket. And when the closing bracket will encounter, we'll match it with the opening bracket and we'll pop it. So it is Q1, closing bracket, opening bracket, it is Q1 null. Now, at last, when we have used all the elements, it is Q1 null Z0, it will give us Q0 Z0. So here we are writing Q0 Z0. There is a specific reason for that. That we have only one accepting state here, and that is Q0. Q1 null Z0. Q1 null Z0, that will give us Q0 Z0, where Q0 is the accepting state. So let us see that why we are writing like this. Now you can see this Q0 opening bracket and Z0, Q0 opening bracket Z0. So from Q0 we'll go to Q1 state because Q0 is the accepting state. We'll change the state to Q1 and we'll push opening bracket on the stack. So opening bracket Z0. Now we have a Q1, we have a closing bracket and opening bracket. So we have a pop operation. Closing bracket will match with the opening bracket. We have Q1, opening bracket, closing bracket, and Z0. Now we have already matched one opening bracket with one closing bracket. Right? So effect of that is nullified. We have already matched one opening bracket with the closing bracket. So that effect is nullified. So now what we have? We are using Q1 null Z0 because we want to restart the process. So Q1 null Z0. We'll consider this last rule, Q1 null Z0. And to restart the process, we'll go to Q0 state. Q1 null Z0. We'll go to Q0 state. We have a Q0, a pair of brackets, and Z0. Again, we have the same thing. Q0 will convert to Q1. We'll push opening bracket on the stack. So it is Q1, closing bracket, and then opening bracket Z0. Again, it is a pop operation. We'll match closing bracket with the opening bracket. So it is Q1, null, and Z0. Now Q0 is the accepting state. So from Q1, we'll go to Q0, Z0. So now you can see that why we are going to Q0 state again. Because we want to repeat the same procedure several times. And that is because of this production S gives SS. We are able to repeat the procedure. Okay, now, is this a deterministic PDA? The answer is yes, because you can see in the move column, we have only one rule. We don't have two different alternatives like push and ignore. In the move column, last column, we have only one rule. There are no two rules together. Second thing, with the null we have state as Q1 with null input, the state is Q1 and top of the stack is Z0. So this Q1 and Z0 are not with any another input alphabet. So these two symbols are not with any another alphabet in any rule. So with null input, we have state is Q1 and top of the stack is Z0. So this Q1 and Z0, you can see Z0 is there, but Q1 is not with it. Q1 is there, but Z0 is not with it. So this Q1 Z0 combination are not in any other input alphabet in any rule. So it is a deterministic PDA. We don't have to generate multiple paths, or we don't require a fork system call because there is only one unique path. We will never get multiple alternatives to try in the deterministic push down automata. Okay, so now let us proceed further. I hope this is clear now that what is a deterministic PDA. So you can see here the example, right? If we treat opening bracket as A and closing bracket as B, let us assume that opening bracket is A and closing bracket is B. So we are able to push A, right, on the stack. First, we'll push the second A. When B will encounter first B, so closing bracket will match with the opening bracket. And similarly, second closing bracket will match with the another opening bracket. If it is BABB, so this BABB will not work because B is a closing bracket. Because B is a closing bracket, so it will not work. Clear? We don't have any such rule. We don't have any rule like Q0 closing bracket, so it will not work. Okay, now here we have one more deterministic PDA. We have one more deterministic PDA. Right? Number of A in X is equal to number of B in X. We want equality of A and B. We want equality of A and B. But the order is not fixed. AB is valid, BA is also valid. Is it clear? AB is also valid, BA is also valid. So can anyone tell that what we are doing in this deterministic PDA? The first symbol can be A, second symbol can be, first symbol can be B also. But again, we have equality of A and B. It is a deterministic PDA, so Q0 will be the accepting state. Always Q0 will be the accepting state if null is a valid string. If null is valid in deterministic PDA, then Q0 will be always the accepting state. If null is valid in deterministic PDA, then Q0 will be always the accepting state, as you can see here. So when we are pushing A on the stack, we are changing the state to Q1. Similarly, when we push B, the first symbol, we are changing the state to Q1. When A and A is there, it is a push operation. When B is there, B and B, it is again a push operation. But when AB encounters or BA encounters, when A is in the input and B is on the top of the stack, or when B is in the input and A is on the top of the stack, when both are opposite, input and top of the stack. When input and top of the stack are opposite, at that time, we will perform the cooperation. So if there is a equality of A and B, then at the end we'll get null. So Q1 null Z0, it is Q1 null Z0, and that Q1 null Z0 will give us Q0 Z0. This Q1 null Z0